Welcome to Quantum Curious. And in today's lecture, I'm going to discuss a very important concept that is the concept of the probability distribution of the field. So, in the previous lecture, we reviewed some concepts like correlation functions and how can we infer some properties like anti-bunching and bunching of photons of the field uh, from the values of the correlation functions. And then we saw that how the two-level system is an ideal source of the anti-bunched light. And in the last, we saw that how the quadrature components of the field follow the Heisenberg uncertainty principle, and uh, as these are the only degrees of freedom of the particular mode of the field. So in this lecture, we will see that how these concepts imply for the field knowing only the probability distribution of the field. So we will start with a question like we have some lack of knowledge about the state of the field, or we do not know the explicit form of the quantum state that we are dealing with. So given the probability distribution of the field, we can still infer some statistical features and properties of the field. So, like we want to know the expectation value of the photon number in that particular quantum state, but we do not know the explicit form of the quantum state. Like it is a thermal field, but we do not know its explicit form, but we know the probability distribution of the thermal field. We can still calculate some statistical properties of the field, and we know that we can calculate the statistical moments of the field uh, of or some properties uh, uh, from the statistical moments uh, if we know the probability distribution. So in this lecture, I will go through the thermal uh, field and its distribution, and we will see that how some properties of the field can be inferred from the concept of the probability distribution. And in the next lecture, we will go through another distribution, that is the Poisson distribution. So there is a thermal distribution, and we know that the thermal field follow the Boltzmann distribution, and we know that the Boltzmann distribution is the gives us the probability of a system in thermal equilibrium with in some kind of energy state. So here x is equal to h omega over kBT, and we will see that how can we use this kind of probability distribution to infer some properties of the thermal field. So there is an example. So our goal is to write the previous probability distribution function in terms of the mean photon number. So in some uh, cases, this is the desired form because uh, in experiment we are dealing with these mean number of photons and some variances or fluctuations of the photons. So this form of the probability distribution is quite desirable. So we will start first simplifying this sum that is in denominator, and we know that it is a geometric series and it is a convergent series, so we can calculate its partial sum. So here's the formula of the partial sum of any infinite geometric series that is convergent, and here A is the first term of the series, and R is the ratio of the consecutive terms of the series. So in that case, we can calculate easily these values and calculate the partial sum of the series. So putting this value in Boltzmann distribution, we get this value. So again, simplifying further, uh, we take out the, or we can uh, we can do like moving this e power minus x into denominator, and that will become e power x, and then uh, further simplifying we can get this form. So again, uh, uh, moving down the negative power exponential, we can get this, that is ex power n plus 1. So in order to get desirable form, we have to make up some mathematical manipulation, and we will multiply and divide the denominator and numerator with e power x minus 1, the whole power n, and further simplifying, we will get this form. So this can be easily obtained, and we will see that how it is helpful in calculating this type of form. So now we will see that how we can uh, prove that the mean photon number can be written in this exponential as an exponential function. So again, calculating the mean photon number from the probability distribution function of the thermal field, and we boil down the problem to the evaluation of sum, that is the product of the n exponential of power minus nx. So we know that it is also the geometric series, and we can calculate the sum by some trick. We know that the sum of the e power minus nx series has that particular form, and we know that the derivative of the negative derivative of the e power minus nx has the value of n uh, product with e power minus nx. So putting the value of the partial sum of this particular geometric series, uh, we can calculate the sum of the n product of the uh, n exponential power e minus nx. So putting this value in the expression of the mean photon number, we get this form. And further simplifying, we can see that the mean photon number is just equal to 1 over E x minus 1. So we see that it is just the form that we desired earlier. So we can write the probability distribution function of the thermal field in terms of the mean photon number. And this, as we uh, mentioned earlier, that this particular form is quite desirable from the experimental point of view, because we are in experiment usually dealing with the expectation value of some properties like number of photons. So now we will calculate the fluctuations of the photon number or fluctuations of the thermal field, and we know that the variance is equal to the expectation value of the n square minus the whole square of the expectation value of n. So we know that we can calculate the n square, that is the second statistical moment of value n, with the help of the probability distribution. And we saw that the probability distribution we are dealing with in case of thermal field is the Boltzmann distribution, uh, like and we are we have to evaluate the sum, that is the geometric series of n square, product of the e power minus nx. So again, we will employ similar technique that we employ in calculating the sum of the n product with e power minus nx. So again, taking the second order derivative of this value, we can get the sum, that is the desired sum, that is the product of the n square and the exponential e power minus nx. So putting this value in this expression of the second statistical moment of n, we get this form. So further simplifying the rational function of e power x, we can simplify this rational function with the help of the concept of the partial fractions. So in order to find the value of a and b, where a and b are the constants, we have to solve this equation. So I will left this as an exercise or as an interesting assignment. So we can calculate this these value, and we are end up with the value of a is equal to 1 and b is equal to, and putting this value again in the above expression, we end up with this value. So we know that 1 over Ex minus 1 is the mean photon number in case of the thermal field. So 1 over Ex minus 1 whole square will be the square of the mean photon number, and we can write these expression in terms of the photon number, mean photon number. So we get the value of variance as the sum of the two terms, that is the mean photon number and square of the photon number. So from these value, we can calculate various interesting properties and or quantities. And one of the quantities is the second order correlation function. And this correlation functions defines or describe the correlation of the field at particular moment and particular positions. So we saw that in previous lecture that how the correlation, that is a second order correlation function, can be written in terms of this variance and the mean photon number. So putting the value of the variance in that form, we can get get the value of the second order correlation function in the case of the thermal field. So we can see that it has value uh, greater than 1, and to be specific, it has the value of is equal to 2. So we saw that the correlation function having value greater than 1 would have the tendency to show that the field has bunching of photons. So it is saying that the probability of detection of two photons together is much higher than detection of the individual photons. So the thermal field or chaotic field or the field from the sources like star and incandescent bulb would have would have the field that have properties of bunching of photons. So we can see that the benefit of the uh, or power of the distribution function, and how can we infer some interesting properties like calculating correlation function from mere the concept of the probability distributions. So this technique is quite and this concept is quite powerful and beneficial. So thank you. And in this lecture, we saw that how the probability distribution function is quite helpful in inferring and getting some insights about the properties of the light. And we saw in particular for the case of the thermal field and how we can infer some properties like bunching of photons in that case. So in the next lecture, we will see that how can we infer similar kind of properties from the Poisson distribution.